need to discuss the weakness of using the x-intercepts when we have graphs. Look at this graph here. It doesn't have any x-intercepts. Can we really use the x-intercept form when we have that problem? But we do have another way of doing it, and that's using the vertex method. And the vertex method hinges on the equation y is equal to a times the quantity x minus h squared plus k, where h and k are the x and y coordinates of the vertex respectively. And here's the process of this method. We're going to plug in the coordinate points of the vertex into the equation. We're going to choose an easy to determine point to solve for a, and after doing that we're going to resolve the equation down into y equals ax squared plus bx plus c form. Let's look at our first example and try to determine the equation for the graph. I'll change the axes so it's easy to read. And here's the graph. First thing we need to do is read off where the vertex is, and I claim it occurs at the coordinate point 4, 4. So let's input that into our equation. So we have y is equal to a times x minus 4 quantity squared plus 4. Okay? Next, we need to pick an easy to read off point to solve for a. And looking at this, I think an easy point to use would be the coordinate point 3, 5. All right? So let's input that for our x and y values. Y will be 5, x will be 3. And so our equation becomes 5 is equal to a times the quantity 3 minus 4 squared plus 4. Now let's solve for a by doing simplification. So we have 5 is equal to a, okay, the interior of that will become negative 1 squared plus 4. We'll simplify a little bit more. Negative 1 squared is 1, so we have 5 is equal to a plus 4. And we'll subtract 4 from both sides to isolate a, and we'll have that a is equal to 1. Now that we have this, let's finish solving for our equation. We'll input that into our vertex form. So we have that y is equal to x minus 4 quantity squared plus 4, and now we simplify. We're going to FOIL that x minus 4 squared. And I'm going to do a nice little simple trick because I know it's a perfect square, so it becomes x squared minus 8x plus 16 plus 14, or excuse me, plus 4. I can drop the parentheses because I don't have any weird number multiplying, and so I have x squared minus 8x plus 16 plus 4. I add the 16 to the 4 and I get 20. Then the equation becomes y is equal to x squared minus 8x plus 20. And we're done. Now, one more example. Here's the graph, and we need to find the equation for it. We can see that the vertex occurs at the point 2, 6. And we're going to input that into our vertex equation. So it becomes y is equal to a times x minus 2 squared plus 6. Now we need to pick a point that's lying on the graph and it's easy to read off. Here I'm going to use the y-intercept because it's nice, and it occurs at the point 0, negative 6. And I'm going to input that to our equation and solve for a. So I have negative 6 is equal to a times the quantity 0 minus 2 squared plus 6. Excuse me. I'm going to simplify the parentheses a little bit, so it just becomes negative 6 is equal to a times negative 2 squared plus 6. Negative 2 squared is 4, so the equation becomes negative 6 is equal to 4a plus 6. I'm going to subtract 6 from both sides, so I get that negative 12 is equal to 4a. I'm going to divide both sides by 4 to isolate a, and I have that a is equal to negative 3. And it should be negative because the parabola opens down. Okay? Now that we have a, let's input this into our equation and get it into our general form. So we have that y is equal to negative 3 times the quantity x minus 2 squared plus 6. I'm going to FOIL the square. So I have y is equal to negative 3 times x squared minus 4x plus 4 plus 6. Now I need to distribute the negative 3 into that parentheses, into that quadratic that's sitting in there. So it will become y is equal to negative 3x squared plus 12x minus 12, and then we have our plus 6 who's tagging along for the show. And now we're just going to add the plus 6 to the negative 12, and we have that y is equal to negative 3x squared plus 12x minus 6. And that's our equation. And we're done. Now, let's talk about the weakness of the vertex method. Sometimes determining the coordinate point for the vertex is difficult. And also finding a point to use that's nice to determine A is also difficult. It's one of those hit or miss things. Now that we've done this the algebraic way, we need to be able to describe a graph verbally so that somebody can look at the description and be able to draw the graph. And we're going to draw the concepts again from Module 4, Lesson 1, heavily. The trick to this is to give the minimum amount of information necessary to draw the graph properly. Let's work through a couple examples. Here's our first graph. And let's take a minute to look at the graph and determine the information. And here's a chart that I'm going to show you, the attributes and where they're located at. So first off, I'm going to show you where the x-intercepts are at. I say they occur at the coordinate points negative 6, 0, and at the origin, 0, 0. The y-intercept is also at the origin, 0, 0. The vertex of this equation is at the coordinate point negative 3, negative 9. The axis of symmetry occurs along the line where x equals negative 3, and it's a minimum value at negative 3, negative 9. I'll go through some good combinations and explain to you why they're good. Here's my first description. The x-intercepts occur at negative 6, 0, and at 0, 0, and there's a minimum or a vertex at the coordinate point negative 3, negative 9. Here we have enough information to use either one of the previous algebraic methods to solve for the actual function. We can use the x-intercept method and use the vertex as the point we use to solve for A, or we can use the vertex method and use one of the x-intercepts to solve for A there. Here's another description. The vertex occurs at negative 3, negative 9, and the y-intercept is at the coordinate point 0, 0. Here again, we can use the vertex method, and we'll just use the y-intercept to determine A. It's a pretty easy, simple one. Here are some okay descriptions that are good, but not enough to give us an exact function. The x-intercepts occur at negative 6, 0, and at 0, 0, and the axis of symmetry is along the line x equals negative 3. First, let's look at the graph. The x-intercepts are in the correct place, the axis of symmetry is in the correct place, but hold on, let's look at a family of graphs that satisfy this information, and here's the graph. Each one of these quadratics have x-intercepts at negative 6 and 0. Their axis of symmetry is all along the same line, x equals negative 3. That's the problem. We don't have enough information to have the correct form. And here's another lacking example. The x-intercepts occur at negative 6, 0, and at the coordinate point 0, 0. It also has a minimum value. Now let's look at a family of graphs that satisfies the information we're given. And there's quite a lot of them. I've changed the axes just a bit so you can see them. And we can look at each one of these graphs and see that the x-intercepts occur at the proper location and that they each have a minimum value. Yet, because all of these graphs follow this information, we don't have enough information to provide the correct function to model that red graph that we've got. And that finishes that example. Now, remember when trying to describe graphs verbally to provide enough information to be able to use the algebraic methods we described earlier. Okay? That wraps up looking at the multiple representations of quadratics. I'll catch y'all next time.